recursion, not recursion, that's, what do we call it? The formula, use the previous term to define cell, it's, what is it called? No. Yeah, there are three ways. One is induction, one is like a tree, right? The third one is the method theory, right? Okay, but I forgot what's the formula called? Recurrence is the type of program. That's where that formula came from. Okay, but yeah. But anyway, yeah, you guys, can check out the previous chapter. But anyway, okay. So today, okay, we are going to focus on divide and conquer. So this chapter obviously is the source of the formula that we saw last week. Okay, so we are going to talk about what is divide and conquer and a number of examples for the divide and conquer algorithm. So divide and conquer basically is a strategy to design algorithm. Okay. This paradigm, okay, has three steps. The first one, you divide the problem, okay, into subproblems, usually with a smaller size, okay, and then you try to conquer, basically solving each subproblem recursively, okay. And the third step is, once you have the answer of these subproblems, okay, you sometimes need to do some work to combine the solutions of these subproblems, to become the solution of the original, problem of a bigger size. Okay, so for these three steps, okay, usually, okay, the cost, of course, the time, when we say cost, usually we refer to time, okay. So the most time, okay, can be in any steps, okay. But in terms of programming, the second step is usually the easiest one, because you solve these subproblems recursively. What do we mean by recursion? Basically, you just you just do a recursive call, and let the recursion take care of these subproblems. So basically, you just rely on that, and you don't need to write a lot of program. So which is nice, obviously. But the first step and the third step sometimes, okay, require certain work. Okay, in other words, most of the time, your program, okay, is a little bit more complicated in either the first step or the third step or both. Okay, so having said that, let's look at some examples of this divide and conquer algorithms. The first example that, actually we have seen that in the first chapter is the merge sort. Okay, in the merge sort, okay, you try to divide a problem. If the problem size is 1, it is already done, right? As I have mentioned to you guys, if you have one number, that number must be sorted, right? So that's base case. That's that's where the recursion terminates, okay? But if the problem size is greater or equal to 2, then first you divide the problem into 2 parts, okay, of roughly equal size, okay? That part is trivial because we use array, right? So you just find the middle element and try to send like the first half, and try to treat the first half and the second half as like 2 subproblems. Okay, and then the conquer, okay, you just recursively solve 2 subarrays. So in this place, as I said, you just let the recursion do the work. So just very simple recursive code, really nothing complicated. Programming wise, okay. Of course, like when you really go down, okay, into the recursion, a lot of works need to be done there. But in terms of reprogramming, of course, just like 2 recursive calls, okay. And then once you have like 2 sorted sublists, we need to combine them into 1 single sorted list, okay. That is like where the merge sort spend most of the programs in the merge sort, most of programming in the merge sort take place. You have several number of lines for the merge part, and as we have discussed, in the first week, okay, it takes linear time to merge these 2 subarrays, okay, or 2 sorted sublists into 1 single sorted list. Okay, so in this example, first, the divide is trivial. The combine is the part that is a little bit more complicated. Okay, but the second step is usually what I said, just a number of recursive calls. Okay, and in this example, one more thing to mention. Okay, we divide the problem into 2, right? Is it always the case we divide problems into your problem into 2 parts? Yes. Okay, most of the time, but sometimes it's not necessarily the case. Okay, in more general description. Okay, let me come back here. In more general description, okay, in the first step, you divide your original problem into n subproblems. Okay, this n usually it will be 2, but in some other occasions it could be more than 2. Okay, and in the second case, the second step, we need to conquer the subproblems. Okay, so how many subproblems that we need to solve? This is also an interesting question. Okay, so remember in the first step, the general term, we divide the problem into n subproblems, right? But in the second step, we usually, in the worst case, we need to solve every single subproblem, right? Okay, but sometimes, okay, if we get lucky, in some special occasions, we only need to solve part of these subproblems. So, in other words, in the second step, okay, we need to solve some subproblems, but the number of subproblems we need to solve, okay, will be n. This n usually is smaller or equal to n. Okay? You may ask, how about if we need to solve more than n subproblem. Is it possible? Yes, you could do it that way. But if that's the case, usually you lost the advantage of divide and conquer. Because if you, I mean, we have a particular algorithm design paradigm. The purpose is to write an efficient algorithm, right? So if at the end the program is not efficient, then you lost the benefit of like designing your program this way, right? So basically, so yeah, you divide the problem into a number of subproblems, and in the conquer you solve, make it like a little bit simpler. Okay, you solve some of these subproblems, solve some of these problems, and then in the combine you try to put together these solutions and try to solve the original problem. So basically, just want you to understand. So this one, in the merge solve, we divide the problem into two. Conquer, we need to solve both of these two subproblems, and then we combine it. Okay, so this is like the merge solve that we talked about in the first lecture. How about the other example? Not working. So, in terms of the time complexity, you write it like a T of n equal to 2 times T of n divided by 2, okay, plus theta n. So in this, recurrence relation, I'm sorry, I forgot like the term of this type of, formula, okay. Anyway, here, n divided by 2, okay, this denominator usually indicate, or n divided by 2, this denominator usually indicate the size of your subproblem. Okay, and this 2, okay, means the number of subproblems you need to solve recursively. Okay, and here is the cost for you to either do the division or and the combination, the first step and the third step. But in the merge solve, really like the divide only takes constant time, so it is not considered. But because like the combination itself takes linear time. Okay, but in other occasion, okay, maybe the combine is trivial, but the division, the divide is complicated, as we will see later. Okay. So, obviously, with this recurrence relation, you can apply the master theorem, okay? And where A equal to 2, B equal to 2, your f of n is it's a linear. So, if you try to plot that into master theorem, okay, 2 log 2 is n to the power of 1. So basically they have this one and f of n is of the same order. Okay, I probably, yeah, so basically it is like the second case. Okay. So the result is T of n equal to n times log n. Okay, because like f of n is n to the power of 1 times log n to the power of 0. Okay, it's linear. So that's also case 2. Do we have any other example? Yes. Like we have another very simple divide and conquer example in binary search. You guys know binary search, right? Okay. Binary search works for the array that is already sorted, right? The numbers in the array is already sorted. Okay, once if you know, if you have this assumption that the numbers in the array is already sorted, and you are looking for a particular number, you can use what we call binary search. I suppose either like a data structure. I mean, you should have learned that from data structure, or even earlier, like in your like a freshman year. Okay, so in the binary search, basically it is also divide and conquer, because first you find the middle element of your array, right? And compare to the number that you are looking for. Okay? So that is the divide. Okay, check the middle element. And from there, okay, if the result will give you either smaller or greater, right? I mean, if it's smaller, maybe you go to the left side. If it's bigger, you go to the right side. If it happens that middle element is what you are looking for, then you terminate, right? You terminate. Basically, you found it. Okay. So think about this. So that conquer actually, okay, means that you need to recursively search only one subarray, right? So this is an interesting example, because like the divide will break the original array into two subarrays, and in the conquer you only need to recursively work on one subarray. So A is, now like A is 1 instead of 2. And then combine is trivial. Basically, like you keep doing that, just either you find it or if you don't find it. If you find it, that means like the middle element is what you are looking for. There's a match. If you keep doing that, and when you exhausted all the elements in a particular area, and that means like you couldn't find any match element. So basically, the binary search, first, you need to understand that it is also a divide and conquer algorithm. Second, okay, you divide the problem into two parts, and you need to only recursively deal with one of them. So let's have a little bit of an example. Okay, say you want to find 9 in this array, and obviously in this array all the numbers are already sorted. Okay, and then first you try to compare 9 with the middle element. So the middle element is 8. Okay, is 8. So 9 is greater than 8. So obviously, if 9 exists in this array, it must appear on the right hand side. So that is, you do a comparison, it is not a match. So you can cut the search space in half. So in other words, you only need to focus on this half. Okay, so you only need to recursively search one subarray. Okay, and then you try to compare 9 with the middle element, which is 12, and then obviously 9 is smaller than 12. So again, you can cut. The other half. Okay, just leave like this part. Okay, and then the last step, compare 9, the number you want to look for, with this because you only have one element here. You do the comparison and there's a match. If at this moment there's no match, you exhausted all the possible elements, then, just report the number is not found. But in this case, 9 happened to be there, so, yeah, that's it. So this binary search, okay, obviously, okay, the formula will look like this. T of n equal to 1 times T of n divided by 2. I mean, every time we, compare with one element, okay, we break the problem into two halves. Okay, so of similar size, to be exact, it's n minus 1 divided by 2. But it will be, roughly n divided by 2. Okay, so we just write like T of n divided by 2. But we only need to deal with one of them. So A becomes 1. B, n divided by 2, the problem size is the subproblem size. And then plus theta 1, because, they are, in the divide, we only need to do one comparison. That one comparison helps us to break the problem into subproblems. But that one comparison takes constant time. Okay, so that's it. There's really no merge. Okay, there's really no merge part. So this is like the recurrence relation. And if you try to apply the master theorem, because B is 2, A is 1, so obviously n to the power of log 2, 1, it will result in 1, the constant. And this 1, it happened to be this, symptotically, the same order to your, theta 1. Okay, so then it's the log n. Again, it's case 2. Okay, so this should be trivial. Okay, should be trivial. After all, like you guys should have learned like a binary search, either from data structure or even from like earlier courses. Okay, and then powering a number. Okay, this is actually a problem. I used to teach discrete math. Okay, I taught discrete math for maybe 6-7 years. Okay, before taking over the department chair, and then because I take over department chair, so I try to switch to algorithm and linear algebra. So basically, like I know pretty well what discrete math covers. Okay, so this is a problem that is covered by discrete math. So supposedly, I can assume you guys should have learned this in discrete math. If not, then your discrete math professor may have some issue. Who is your discrete math professor? 小光。蔡老师。Okay. Okay. I remember because when I teach like this, when I taught discrete math, like I taught one section, like Professor Tsai taught another section. Okay, so I remember he usually teach like the subject like in different order. Okay, but he should cover this part. Okay, by the way, so if you compute a to the power of n, okay, where n is a natural number. Okay, natural number just means like 0, 1, 2, blah blah blah, like the positive numbers. Okay, so the naive algorithm will give you linear time. So if I ask you to write a program, okay, in a naive way, how do you write it? It's a loop, right? it is a loop. So every time you go through a loop, you multiply this number by A, right? Okay, so this loop runs n times. So you get like a to the power of n. Of course, you need to initialize this number as a 1, right? So that's the basic idea in the naive approach. Okay, and obviously, because you will run this loop n times, so it is obviously linear, right? So far so good. So everyone, no problem, right? But how about if we try to use divide and conquer to deal with it? Okay, the idea is like this. We know a to the power of n, where if n is even, then we can solve, we can compute a to the power of n divided by 2 times a to the power of n divided by 2. We know it is going to be like that, right? Okay, how about if n is odd? Yeah, if n is odd, then it's going to be, like this. A times a to the power of n minus 1 divided by 2 times a to the power of n minus 1 divided by 2. Because well, n minus 1 will be an even number. Okay, so of course, you also have a base case. Okay, the base case is a, when the power is 0. If the power is 0, then a to the power of 0 is 1, right? You terminate this recursion. So when you write a program, to make use of this recursion, okay, recurrence relation, it should be obvious, right? The only thing you need to be careful is that, okay, when you call recursive call to solve this part, remember, you don't call recursive call twice. We call recursive call here, okay, and then multiply and another recursive call, the return value of another recursive call. This is wrong. This is wrong. Okay, and because this number and this number basically the same, right? So you just call recursive call once, and then after you get the result, just square that result, right? And you get the same thing, right? So you don't need to call recursive call multiple times. If you do recursive call multiple times, including this one, if you do recursive call multiple times, it's going to hurt the time complexity. The algorithm will be correct. You still be able to calculate a to the power of n. No problem. The answer is correct. The issue is time complexity. Okay. Anyway, so if you use this recurrence relation concept to design the algorithm in the right way, okay, your recurrence relation should look like this: T of n equal to T of n divided by 2 plus theta 1. This one is exactly like what we have for the binary search. Okay, this n divided by 2 is our subproblem. Either this one or this one. They are similar to n divided by 2. And we have we only need to solve one subproblem. This is because, as I mentioned to you, we only need to solve one of them and then square the result. Okay? If you don't do that, if you try to, have recursive call for this one and then have recursive call for this one and then multiply the return values, what happens is that this one will become 2, right? If this one is 2, look at the master theorem. Time complexity will be different. The time complexity will be different. Okay. So anyway, so for this one is T of n is theta